Today we're going to be learning about geometric sequences in series. Our objective is that we'll be able to recognize geometric sequences in series, and we will apply formulas to find missing information about geometric sequences in series. A geometric sequence follows a pattern of multiplication. The ratio between any two consecutive terms is always the same, and R stands for our common ratio. So let's determine if these sequences are arithmetic, geometric, or neither. So here we're going from 1 to -4 to 16 to 64. Well, 1 times 4 is 4, 4 times 4 is 16. Now if we want it to alternate with that negative, that looks like we're multiplying, so it's geometric. And our common ratio would be -4. So there's no way to multiply, well, there's a way, but we go from 2 to 5 to 10 to 13. Well, 5 to 10, that's either times 2 or plus 5. Well, 2 times 2 does not give us 5, and 2 plus 5 doesn't give us 5. 10 times 2 doesn't give us 13, and 10 plus 5 doesn't give us 13 either, so this would be neither. So it still could be following a pattern because it looks like it adds 3, then adds 5, then adds 3. So the next one could be an add 5. There's still a pattern happening, but it's not an arithmetic or a geometric pattern. Here we go from 3 to 6 to 9 to 12. So we're adding 3 each time. Arithmetic. And the common difference is 3. So this is our formula for a geometric sequence. Again, this is on the SOL formula sheet that you get to use on this quiz. So find the nth term. That means write the equation, write the rule, given the sequence. So we need to know a sub 1, and we need to know the common ratio. Our first term is 4. We are multiplying by 3 each time, so that's our common ratio. So A sub n equals 4 times 3 to the n minus 1. In number 5, we're given the third term, not the first term. So we need to find the first term. We know the common ratio. We could plug in to the formula, so we could say -12 is a sub 1 times -2 to the 3 minus 1 power. -12 is a sub 1, -2 squared, which is 4. Divide both sides by 4. Get a sub 1 is -3. The other option is, if our pattern is multiplying by -2, we go backwards, it's dividing by -2. So -12 divided by -2 would be 6. 6 divided by -2 would give us a first term of -3. Again, either way to find the first term is fine. So a sub n equals -3 times -2 to the n minus 1. So that's dealing with our sequences and writing a rule for our sequence. There are actually 2 different types of sums that we're going to find with geometric sequences. The first is a finite sum. It gives us a certain stopping point. Again, you can use the formula, or if it's in sigma notation, you can type it straight into Desmos. So like number 6, we can do it. There's our a sub 1. It's 2. A common ratio, we're multiplying by 4 each time. And then it gives us n is 12. So s of n equals 2 times 1 minus 4 to the 12th power, all over 1 minus 4. Or if we want to write it in sigma notation, that's a terrible sigma, but we start at n is 1, we go to 12, and our pattern is 2 times 4 to the n minus 1 power. And we go to put these in Desmos. The first one we had. 1 minus 4 to the 12th. Over 1 minus 4. Gives us 11,184,810. Or if we use the sigma notation, starting at the first term, into the 12th, of 2 times 4 to the make sure you put parentheses around the n minus 1, or yeah, the n minus 1 in Desmos, because if not, it's going to try to bring your minus 1 down out of the exponent. But either way, we get the same answer of 11,184,800. So we could take this, plug it into the formula. First term is 1/2 times 1 minus 6 to the 10th over 1 minus 6. Or we can just type it into Desmos. See, there we go. I forgot to put the parentheses right after I told you all not to forget the parentheses. So this one comes out to 6,046,617.5. And yes, we're even going to include that 0.5. So that's a finite series. That's when it's S sub n. We also could see S sub infinity, which means the infinite geometric sequence. So it's saying if it goes on forever, what is it going to add up to? This only works part of the time. It only works when our ratio is less than 1. So here, we go from 3 to 6 to 3/2 to 3/4. We're dividing by 2. Which means our common ratio is 1/2. Okay. If we wanted to write this in sigma notation, n equals 1, we'd have infinity, we'd have 6 times 1/2, the n minus 1 power. Or we can just use the formula. First term over minus r. So one weird thing about Desmos is it does not like putting the infinity symbol up here to type it in. So I'll show you how you can make it work. So we're going to go from 1. I'm going to put in my formula first. Okay. And up here, I need to put a very, very big number that's like we're going towards infinity. So I'm just going to keep putting in lots of 9s. And eventually, so at the beginning, like when now it's not going to like it. Let's switch. Oh, goodness. Sorry. Okay. So I'm going to put lots. When I put just 1 9, it gives me a decimal answer. Once I put a second 9, it goes straight to 12. Or once I keep putting more and more 9s, just like it's 12. Okay, so instead of infinity, you're just going to put lots of 9s. Or you can type this formula, which will come out to be also 12. So let's try the next one. 1. Formulas. Nine. Okay, I was having this problem earlier. Alright, so when I put in 1 9, it gives me an answer. Another 9. If I keep going, it eventually tells me it's undefined. Why is this happening? Well, our rule said we can only do infinite if r is less than 1. Our r is 2 here. That's greater than 1. So therefore, the infinite sum does not exist. Okay, and this happens anytime r is bigger than 1. That's all for today. Fill in your summary, and I'll see you in class.